Ja. Tsch.
Skulle du meget gerne være der. have den der til at starte med.
Ja, det synes jeg er en rigtig god idé. Og så har vi også sådan en...
Giver den bare til dig. Emil, så får du den.
Jeg skal bare have en klips. Du skal have en klips, ja. Og Emil?
Og så bare ned i en bukselomme her bag.
Ja, ikke? Og det der led, det er lidt svagt. Så det skal helst sidde frit, så en bukselomme er lidt dårligt. Det er bedre, hvis du klipser den fast, så den sidder lidt frit, ikke?
Jo.
Sådan der. Det er skønt. Hvad hedder det? Har vi testet det her? Ja. Og den her? Ja.
Der er stadigvæk det problem med.
Ja.
Der er stadigvæk det problem med en taler, der tror, han kommer til sin laptop på.
Ja, det kan det ikke.
Nej, men det, han bare har brugt 20 minutter sammen med en eller anden.
Men det må I lige klare sammen og se, om det kan lade sig gøre.
Jamen, altså allerhelst så vil jeg jo... Der.
Nå, men det er det, vi snakker om. Styrke til at stå med noget stille. Vi snakker lidt.
Yeah, but you know, it takes a while and because of the streaming and stuff. Fornans.
En, to. Jeg starter lige med at sige til ham.
Det må du meget gerne.
Tak. En, to.
Sådan der.
Rigtig
Jeg ved ikke, om den kan sættes fast her i kraven måske. Slipsen måske.
Typisk.
Så tæt på munden som muligt.
Ja. Men
Skal vi hjem?
sådan der. Det er vist godt. Ja.
Det tror jeg.
Agtigt.
Og så ved jeg ikke, om du har en lomme.
Masser. Jepper. Ja, kan man høre noget som helst? Nå, men det finder jeg ud af. Nu er vi heller ikke gået i gang endnu. Hej.
Jeg vil ikke spørge dig om det, jeg vil spørge dig. Det tror jeg spørge dig om. Jeg vil bare høre, jeg skal bare spørge for Gitte, om hende og Dan må komme ind til byen, når I har færdig med at
Var det mig? Hallo? Om de må komme?
var noget med, at du kørte ind til byen, ind til åbningen, hvis jeg...
Nå ja, selvfølgelig.
Hallo?
Så tager jeg en lille bil.
Og den her, den er så lukket lige nu.
Ja, fint. Men jeg gør det på den måde, at jeg kører til Lyngby station og så...
Hallo? Ja, det virker.
Jeg har jo en rigtig bil.
Nå, ja,
Den tager jeg jo lige over til.
Jamen, det kan du sikkert. Ja, men det er ingen problem. Hvad? Ja, også på mit. Så, vi skal vel også lige lade et par minutter.
Så kan folk komme ind, mens jeg står og siger.
Nå ja, det er også rigtigt.
Det går også tid.
Ja.
Det går for din tid. Eller et eller andet.
Du skulle også sige noget om generel housekeeping og mobiltelefoner og alt det som er med.
Nej, der er ikke
har
nogen
lært det.
sessions live, så jeg tror sgu
Nej,
ikke,
det
det
er altid.
springer lidt. Det tager lang tid.
Ja, folk ved det godt.
Ja, gør det det? Det håber jeg.
Ja.
Ej, men jeg kan godt se, at de skal huske at mute deres telefon. Det er måske en meget god idé, faktisk. Hvis ikke de har gjort det nu. Sådan noget. Det gør du, det stemmer med det der.
Nå, det der om. Nej, det mener jeg foran. Det er decideret foran. Jeg stillede dem i går, selvom det mekaniske jeg driver helt vildt. Så. Jo, hvad? Kan du ikke høre mig? Ja, ja. Det er derfor, jeg musser stille.
The official conference time is now 4 p.m. and I'm starting this first breakout session. My name is Dan Mønster. I'm from Unici and I will be chairing the session which has 3 speakers. The session is entitled Networks for E-Science, from the depths of the oceans to the depths of the universe. And of course, if you read the program carefully, you know what lies in between the depths of the oceans and the depths of the universe. That is music from the volcanoes. So I think this will be a very exciting session about some of the projects that use the infrastructure that the research networks provide. Our first speaker today is Martin Beck, who has Master in Engineering and is the Deputy Director in UNICE, where his division is responsible for, among other things, the development and operations of the Danish Research Network and also some of the commercial businesses of UNICE. Martin has been involved in many pioneering projects involving networks here in Denmark, among other things, setting up the first commercial internet service provider in Denmark, deploying nationwide services to schools, and one of the last projects also the health network. And Martin will be telling us a bit more about the Galathea 3 expedition that we heard about in Catherine Richardson's talk, and he will give you some more technical details. So please, Martin.
Thank you. Well, so this is about it. Normally we have the NREN. Wherever we go, we think of it as that way because we have wireless network and so on. But this is actually about taking the NREN around the globe. Galathea 3, you heard about it from Catherine Richardson, so I'll skip the fact slides, and you also know why we call it number 3, because there were 2 before. And the idea was simply to take a Navy ship called Væderen, which means the ram or the star constellation Aries, and take that and transform it into really a research expedition ship. They still kept the cannon to deter pirates, or I don't know why, but instead of having a helicopter flight deck back here, they converted that to have laboratories and so on. And we had 2 roles, actually, as an NREN, we had 2 roles, namely that we provided the network for the ship, network connection from ship to shore, and gave it internet connection, of course, and also a dissemination effort where we were entrusted to make a theme covering all aspects of the Galathea 3 expedition for schools on our national content portal called EMUDK. It stands for the Educational Materials Universe in Denmark. So it has nothing to do with the monetary union or something like that. Okay, it's National Material Portal for schools. And we had a participant on board to do that kind of dissemination. Now, doing a network to a ship is really a collaborative effort. Of course, we didn't put up the satellites. Intelsat did that, and they and a lot of other parts, namely especially the Danish Institute for Fisheries Research, they did all the equipment and networking on board the ship, whereas we did the internet provision, and we did the firewall configuration and operation, of course, and also provided 24/7 support and operation and maintenance and so on for the whole setup, also the satellites. And when you want to use satellites to provide networks to something like a ship, of course, what we want to do is do the best thing possible, the best thing that money can buy. And if you look at it, here we have some different footprints from some of the Intelsat satellites, and you can see there are shaped beams along the, which follows more or less the big land masses up there, and of course the bandwidth obtainable there are higher. But if you really sail on the high oceans, the only thing you need is the round beams, and if you look at them, for instance, down here, actually the route was going to go down into the Ross Sea at the Antarctic, down here at Antarctica, and you see here we come really close to the lines where the line of sight to the satellite from the ship, it's a geostationary satellite, the line of sight is parallel to the ocean or just a few degrees above the horizon. And of course there shouldn't be many icebergs or many islands or anything in the way, then the network connection is lost. And we also experienced that, of course. But this means that once it's simply the shape of the Earth that sets the limit, then we had to go for the non-directional beams, and then the obtainable bandwidth was 1.5 megabit from ship to shore and 0.5 megabit from shore to ship. Now, why is that? Normally, if you are an internet user on the ship, you would want that asymmetry to be the other way around, but it has to do with two things, mainly with one thing, which is economy. Because transmitting and receiving from a land-based station, there you can have a really big satellite dish, whereas on the up here on the satellite, you have to use a lot of power actually to transmit in that direction, whereas you can transmit with a very low power here and still obtain a readable signal because you can just have a bigger satellite dish. Where on the ship, of course, we had a limitation as to how big the satellite dish could be. So that's why, and then the excuse, of course, was that we expect that more results are being transmitted from the ship to shore than the other way around. But another interesting feature of such a network connection is that there's a round trip time of between 600 and 700 milliseconds because there's roughly 150 milliseconds up to a geostationary satellite, and normally a packet has to travel that distance, 150 milliseconds, 4 times, and then you have to add a little for the land-based stations, for instance, on the other side of the globe, like in the California, where we took down the beams from satellites on the other side of the globe. So there's a little land-based distance there as well. Okay, and also we could read from the data sheets from Intelsat that there would be approximately 1% of packet loss, not more. Now, you could say that this is like being at the wrong end of an ADSL going halfway to the moon. And it was actually a new thing for us to imagine. Normally we have good network connections and never round trip times like this. How would the various applications perform in an environment like this? Would video conferencing work? Would we be able to use that bandwidth actually to FTP data home, or would we not? And the only way to find out, actually, because no one really knew much about it as far as we could tell, was to simply build a simulator on the network on board. So the clever guys, my colleagues at UNIC, they took a FreeBSD, this one, FreeBSD box with IPFW and Dominet, and that can be configured so that you can have 1% packet loss or an infinite amount of packet loss. It's configurable. Also, the delay, the round trip time is configurable. So you can tweak and turn and see how much packet loss and round trip time and other parameters, also jitter and so on, will affect your applications. Quite funny, and it's open source. Trying that really was a big disappointment for a lot of guys that had thought that they would have this and that equipment on board. So, quite interesting. Now, that showed us that video and data moving applications such as FTP could only use a very small fraction of the bandwidth. And so we had to do something else. And then we had two options, either to do tuning of every PC, every server that was going to be on board, to have larger TCP window sizes, both, of course, on shore and in land, and also tuning the simultaneous download limit so that you're not, for instance, if you watch, try to download a web page containing 20 elements of graphics, even though it's 0 bytes all in all, you still are several seconds to download it, because first you ask for 1 or 2 of the elements, you get them, then you ask for the next 2 and so on, and before the whole page is downloaded, even though it's 0 bytes or very few, it can take a minute or so in real life. And we also estimated that during the whole voyage, where researchers would come on the ship and off the ship again, and so on, and with all the various equipment, we would have to configure somewhere in the neighborhood of 900 PCs in order to cope with that. And therefore, we went, of course, for option 2, which is to take a link accelerator box that could compensate for that. I'll explain about that. So everyone could keep their configuration. We got it sponsored from this very fine company, a so-called, it's called a river, the maker is called a riverbed steelhead box. And what does it do? Now, if you are on the ship and you send a SYN packet, then of course you should wait for the other end to send you an ACK packet. Think of that, already there, a little less than a second has passed. Now, what this box does is that it sends you right away, before any connection is made to the shore, it sends you the ACK packet, just like that. And then you send a new SYN ACK and it answers just like that, immediately. And then, in the meantime, between the two boxes, there are two boxes, one ship, one shore, it carries the traffic on a UDP-based, some kind of proprietary protocol, and it also does some packing of the traffic, and also it is caching common packet sequence, not like a web cache or something like on a high level, but common sequences of packets, and then you can just, it can just request for sequence number whatever, which is then stored at both ends. Now, all of this could make actually a standard PC able to use most of the bandwidth available. Also in TCP-based applications like FTP or TCP-based video conferencing or whatever. And in some cases, it could even go above the limit. Here we have an MRTG graph. And as you see, this is normal traffic. And actually, on that particular day, it was myself who was on duty doing the watch of this. And I saw this happening. And suddenly, we had 1.5 megabit from, 1.5 megabit from ship to shore. And the green one here is ship to shore. And you can see it rises up to 10 megabit bandwidth. How can that be? Well, I wondered too. But the explanation was simply that a journalist on board had started Kazaa and turned it into a server. And the thing is that most of the world, they want the same bad music, all of them. So the same packet flows went to a lot of requesters at the other end, and that was cached, of course, by the boxes, the link accelerator boxes, and it just went up. And then at this point, roughly, I introduced some firewall rules, and then it gradually went down. And and I called the ship, of course, and it was it was in the middle of the day. They were in South Africa, something like that. So it was the same time zone. I called on the satellite phone to the ship, and you get to speak to the captain on the bridge, simply because that's the emergency telephone. And I told him that he had to talk to a guy downstairs, and I knew who it was, and so on, because I had his DHCP lease. And and afterwards, I said that he will not be able to use the internet until you've called me back and said that you've spoken to him. And he never did use it. And on the ship, to receive and transmit, of course, we had a 2.5 meter dish like this one. You can see this is to get the size of it. You can see there's a man standing here, okay? And of course, this follows the geostationary satellite. It's not gyro stabilized simply. It's just with the DC motors, and then there are accelerometers X, Y, Z. And then some computer that makes it follow the movements of the ship. And it's specified to cope even though the average wave height is up to 18 meters. So this should, and we never lost the connection due to bad weather. on the whole thing, and it was installed up in this blob up here, where they used to have a tactical radar, but it was taken down and then instead replaced by this connection. You can also see that this ball here is actually smaller than the contour that it was designed for. So when you see the ship another time, you'll see a bigger one, so the tactical radar has an even bigger disk. Very interesting. Now, before we could set out, of course the Navy ship had to be modified in a lot of ways. There had to be a network installed, and the laboratories, and the fishery equipment, and so on. And also, for instance, here the water column profiler, where you can get samples of water at different depths, and installing network on the whole ship. And it all had to be all the long wires, all wires above, I think, 5 meters had to be fibers, because otherwise the radiation from a Navy ship would be above some NATO specification. So that's also why we had to have converters from fiber to common copper twisted pair in a lot of sections. Okay, and there was room, or at least room for I think 90 PCs at any time running on the ship. There was 6 laboratories in 20-foot containers, and here we are. Here you can see some of them, and the insides for various purposes, and cold and wet, and cool and warm and whatever, and also external connections for power, of course, but also for taking in seawater and air and samples like that, and of course also to keep the temperature reasonable. You know, shellfish, taking shellfish apart is not as agreeable in 40 degrees centigrade than it is in 20 degrees. But you know, the smell gets too rough. And in each container there's of course an equipment room with a room for the network connections, and also the container of Catherine Richardson was this one, which was a special smaller one, a 10-foot container placed on the side where there was also running continuously, taking air samples and so on. And also, of course, all the equipment had to be mounted safely, and there had to be devices on the network for picking up all of the data. There's continuous measurements of position and pressure and temperature and humidity and water temperature and whatever, salinity and a lot of other stuff. And all those were is collected via a serial cable, and then again, because long serial cables were forbidden, so it had to be converted into fiber. And so there was a continuous measurement of all these data put onto the network, and the network was done by this guy, the sturdy guy here, and from the Danish Fisheries Institute. And yeah, you see at one of the racks on the ship there was 10 such racks, I think. Now, they were ready to set sail, and yeah, and here we have the internet connection. Here, a more elaborate picture. You can always see it in the slides afterwards and study the nitty-gritty details. But the 4 satellites, and as they went round the globe, they used 4 different satellites, and again used internet. And then the funny thing is that all of this, of course, has to be monitored. It has to be, we do surveillance of it, so if someone fails, we can call the right person or fix it ourselves if it's in our power. And then, of course, for that we have a database for which registers all the equipment that we have the surveillance and operation of. And here's one thing from the database that I've always dreamt of writing, which is the physical placement, physical location, Lyngby and the high seas. Now, what did they use this internet connection for? They used it, of course, for all the research data and so on to get that home, but also for the telemedicine emergency service. They had a video conference home to a hospital in Denmark, and it was used several times actually. Not only when actually, yeah, there was shark bites and stuff like that, but usually for minor incidents. And also they used it, of course, for Skype. The crew especially, they loved Skyping home to their loved ones instead of having to, the alternative that the Navy otherwise provides them with is to take a diskette to the radio officer and have it transmitted through the encrypted channels home. But this is so much more fun, doing a video Skype with every evening, talking your kids in and so on, and that could be done. And a lot of other stuff. This is a newspaper article saying that here's a journalist that hasn't gone out of his shack for 4 days because the internet is so good on board. Now, this is all the hardware. Now we just needed to add people. We have Catherine Richardson here saying goodbye, and the ship sets sail, and here we are. And then for the whole of the journey, actually, we had in 261 days, we only had downtime for a few, all in all 2 days, which gives a 99% availability. And so it worked quite fine. Actually, the biggest incident was, no, I'll get back to that, biggest incident. Then, of course, there's nothing as good as, even if the network is very good, there's nothing as good as coming home. And here we are, coming home, and you see the researchers up on the bridge there, and they look happy because now thing is over, and her hair has grown longer, and so on. Now, another thing we did was actually to try to make every school child and their teacher feel that they were on this expedition. And we did that by making a content portal and with articles and stuff from the expedition about the various subjects. And we had one seat on board which was occupied by 4 participants that shared the route, as you can see here. And we had them on extensive courses in how to use all the equipment that we provided them with. And also we have this content portal is called emu, which is also a bird. And we have this fellow such as this, that is a kind of, we use it, yeah, here he is on course actually also learning until he is very tired. But usually we use it as an avatar for the small school children, so that they can identify with him while he helps the researchers actually here take mud samples from the sea floor. He gets muddy in the process. He passes the polar circle and eats with the Eskimos in Greenland, and he also participates in, for instance, man overboard exercises. Here we are. Okay, and then they rush out and save the little guy and give him CPR and everything. Very nice. Okay, and now you can see if you log into EMUDK, you can see the whole film. Okay, and it's very daunting even if you go to 3rd grade. Now, also out there, of course, the crew gets very bored, so they took the poor guy that was during the cartoon crisis, and they took him hostage, you know, and just slided this this printout was just slided in under the cabin door of our participant out there. And here down below, well. Anyhow, what they used it for, of course, was to give Danish schools a chance to include in their daily education, weblogs, video conferences, online experiments, and so on, in what they do in school instead of just reading about it in a book. And for that, we made a lot of educational video out from the ship, blah, 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 they're talking about plankton, and also a lot of other stuff. Here we also had a map where you could see exactly the position of the ship. And a funny thing happened when they came to the first harbor, really. They thought that now we are not measuring anymore, measuring position and air pressure and so on. So they, in order to save diesel fuel, they just shut down that part. And suddenly, from all our monitors, it appeared like the ship has sunk. And we phoned the ship and say, hey, are you alive, and so on. And of course they were alive. And then they say, no, but we don't need it right now. No, you don't, but we do. I mean, where are you now? That, of course, and the route could also be visualized in Google Earth. Here we are in Greenland. And we included satellite images. Here we have plankton and plankton at home. So you can compare the polar ice cap, which is diminishing, and here a lot of other interesting stuff. We have films from the laboratories where we try to take apart plants and basically blend them, and you look for lead and other materials. We had an English side, even in Spanish, and also 5 conferences like this one on another event.
Vi er alle sammen på vej i havn.
Yeah, blah, blah, blah. And then I would just say, I hope this inspires you to take your own network on a research expedition and see what happens, because I can tell you it's hard work, but it can be much fun. Thank you.
For those of you wishing to take your own research network on an expedition, you have a chance to ask Martin questions about all the technical details of how to do it. Yes.
I was just curious about the curricula that may have been developed for the school children along the way. Is that something that would be persistent, that could still be used, beyond this expedition, or is it tied specifically to the expedition?
Yes, we've just gotten additional funding to actually change the material so that, for instance, if you look at something like this project here, just a moment, I'm sorry if you get seasick from this. Now, if you look at a project like this is just taking mud samples from the ocean floor and freezing them and sending them to Copenhagen. There's nothing much really research in that. But once we get funding actually to follow up and put also on the side what came out of the samples you took, what were the results really. And yes, they are, we've just gotten funds for that too. So that'll be done, but of course only in Danish. I'm sorry.
Any other questions?
Well,
no? Well, let's thank the speaker again. So the next speaker is Domenico Vicinanza, I think. Domenico holds a PhD in physics, and he works at CERN, the European Particle Physics Lab, where he works in the grid deployment group. He is also affiliated with the University of Salerno, where he is a co-founder of something called Music Lab, and also responsible for data sonification at the conservatory in Salerno. And in his spare time, I guess it must be, he is also a computer music composer. So please, Salerno, you will tell us about music from volcanoes on the network.
Right, thank you very much. Well, I'm starting immediately spending a few words about why we are so interested in volcano eruption forecasting. Well, basically the main reason is that currently no definitive way, no definitive methods to predict eruption has been discovered or implemented yet. And up to now, scientists are monitoring seismic waves, number and quality of earthquakes, changes in the shape of volcano, and or concentration of certain gases emitted from the cone. Our idea is to try to correlate spectra and melodies that are produced in a particular stage of volcano activity to try to discover a kind of signature tone of an imminent eruption or earthquake. So a kind of musical spectral characterization of earthquakes and volcano eruption using musical quantity, if we can say. The idea is by identifying musical patterns that can war and eruption, it would be so possible to implement a civil protection measure days or even hours before the event. Well, a few words about what data audification or data sonification is. Well, data audification is just the acoustic counterpart of data visualization. So from a mathematical point of view, it's a mapping between a certain data set and a sound set, so something that we can listen. So data audification is already used in several fields for different purposes, mainly for data analysis and data interpretation. It is used by science and engineering. It is used for education and training. It is used for monitoring tasks up to now. And although most data analysis techniques available up to now are exclusively visual in nature, sonic presentation of scientific data could really be as an additional value, so something that we can add to our already existing analysis. So enlarging the capability to dig into the scientific data. Well, sonic representation are then particularly useful when we have to deal with complex data or high-dimensional data, or when we have to face with monitoring tasks. In fact, research has shown that people are quite more confident with pattern recognition using the human errors that we have instead of visually inspecting a graph, for example. Nevertheless, well, in addition to that, music theorists and researchers during centuries have carried out a lot of techniques and methods to detect, study, and classify musical phrases, so musical signals, if you want. So our main idea is to use music as a language, as a description language, and music analysis as a tool to inspect scientific data. Well, let's come to the network and to the grid. Our first experiments involving sound production was carried out using the INFN grid facilities started during the last months of 2003. In particular, in September 2003, we installed an acoustic compiler called C-Sound to produce and convert to work with sounds using the grid. C-Sound is a free and cross-platform product. And the compiler was tested within the new environment, and the results were really interesting, both in terms of efficiency and in terms of quality of the audio file produced. Why do we need the grid? Well, the main answer is that the computing power needed to run sonification data and to analyze pattern is really, really large. And we can think that to create 1 minute of music, we need to process something like 2 or 3 million data. Each minute is taking more than 100 megabytes of this space, and the analysis of the results and so making comparison, it is a really computing and time-consuming activity, taking up to 10-12 hours of CPU. So this is why Grid is a natural platform for this kind of application. And moreover, the possibility, which is naturally granted by Grid with our middleware, to have a distributed database which is shared all over the world, and it is accessible from all the researchers that are interested in that kind of scientific status, will really pave the way for an effective and a coherent interaction among researchers in this field. After a couple of years of research using C-Sounds or using this first version of acoustic compiler, we moved to a Java product, so a Java sound production package that seems to be more flexible and easy to manage. So it is a product developed jointly by the Conservatory of Music of Salerno, the University of Salerno, and INFN Catania. And all the results I'm presenting now have been obtained using this package. So here you can see, for example, an input file used to send the job on the grid. Well, fine. So our sonified data were geophysical data collected by digital seismographs placed both on the Etna volcano surface and so in Catania, Italy, and on the Tungurahua volcano in Ecuador. And in particular, data from Tungurahua are transferred currently from the Ecuadorian NREN to Garo in Italy using the Red Clara network. So it's 622 megabytes per second network, which connects the Ecuador to Gen2. So we carried out basically two sonification. The first one is we call a straight sonification. So basically we take the seismogram, so the digital seismogram, and we converted it into sound and using a resampling factor to make it listenable. And the second one is we call seismogram melodization, so a transformation into a melody. And we are looking at what is meant in the few slides later. So in both cases, what is really important is that the structural properties of the seismogram, so all the information that are in the seismogram, are mapped into sound or melody properties. In the first case, so the straight sonification, the regularities in the seismograms will be reflected into spectral lines in the sonified signal. In the second case, so in the melodization, so in the creation of a melody according to the shape of the seismogram, the regularities in the seismogram will be transferred into regularity into melody in a, for example, a repeated set of data in the original set of scientific data would create a regular melody, so a melody which inherits this kind of regularity. Here we can see a couple of pictures. So this is the waveform created by so reconstructed by our program, and this is the spectrum. This is related to a 10 times resampled signal, so we have to divide by 10 the frequency here to have an idea of the real values. So the order of magnitude of the frequencies of this signal is in range of 0, 50, and they have a central envelope which develops around 25, 30 hertz. So it's a kind of brown noise. So, well, this is the Etna waveform here and sonogram. So the sonogram is the evolution of the spectra with time. It is quite. Thank you. So this is 10 times resampled. And to have a comparison, this is the waveform coming from Tungurahua, and we can listen to it. Okay, so the idea is that spectral lines are related to regular patterns. So studying the evolution of regular lines, so of spectral lines, is providing information about the evolution of the dynamic of the volcano with time. In this case, for example, we can see the evolution of the waveform. So here is we can see an enlargement in the amplitude of the oscillation. And you can even see here the change in the spectrum. So there is a pattern change in the sonogram that is going to tell us something about the physical phenomena which is going on. Let's move to the data melodization. So the creation of melodies according to the shape of our seismograms. The basic idea is quite simple. So the whole data set is mapped on a piano keyboard, and so the minimum value is mapped on to the lowest playable note on the piano keyboard, and the maximum value to the highest playable note. And we can see here a sketch showing how how a melody can be represented by a graph and vice versa. So the main advantages about using this kind of sonification, of melodization, is that we have a huge amount of tools already available for free to manage MIDI file and analyze them from a statistical point of view, trying to discover regularities, linear regularities, transformations, self-similarities, and so on. So tracking the evolution of the musical intervals, it is so possible to detect any kind of modification in the shape of the seismogram. These are the references to two main tools that we used to analyze the result. This is an example coming from classical music, so to see which kind of analysis we can do. So starting from the score, we can track the distribution of the intervals, the proportion of ascending and descending intervals. We can do scatter plots showing the self-correlation of the data, distribution of the intervals, and so on. Even dynamic evolution of the melody. So moving from a tonality to another. So a lot of stuff that helps us to study, to investigate the evolution of the melody with time. Let's come to another example. For example, we have let us imagine that this is the initial set of values that we would like to sonify. This is our graphical representation of the data. You can look at, for example, here we have two identical values, and here we have a small plateau, which is the representation of these two equal values. And this is the melodization, so the melody, which is a musical representation of the same set of data. And you can see here the small plateau, which is related to these two identical values. So this melody is a musical representation of this set of data. So the set is periodic, so it is regular. So the melody is periodic and it is regular with the same periodicity. So we can say pictorially that we can create a volcanic score in the following way. We start from an empty score and we superimpose the shape of a seismogram on the score. We can overlay the shape of the seismogram with notes, with musical notes, and at the end what we have is a musical score that inherits, in its shape at least, the regular properties of the volcanic signals of the seismogram itself.
Why the extra lines?
Well, actually everything is customizable. So this is just a way to represent the concept of overlaying the shape with musical notes. But of course, we can shrink or enlarge the shape of the seismogram to keep it into 1 bar or more than one bars. We can even do, for example, 4 lines, 1 for each instrument. For a string quartet, for example, we can superimpose the shape of a seismogram, and we can play a real string quartet using the seismogram as an input. And so just to have a sonic example, we can listen to this Tung-Rawa sonification. So this is the shape of the seismogram, and you can listen to it to have an idea how the volcano plays the piano. And finally, this is my last slide, with making some comparison with data. So we did some serious comparison, comparing spectra, comparing patterns, comparing spectral evolution with time, and of course we also made some other experiments, putting together information coming from the 2 different volcanoes on the world. So we put together music coming from Mount Etna in Sicily and Mount Tung-Rawa in Ecuador, and we let them play 2 instruments, piano and guitar. And so what we are listening now is a kind of duet, so it's a concert played by 2 volcanoes in 2 different places of the world, and the medium is the Red Clara and Jean network that allowed us to play together the volcanoes. This is Etna, and this is Tung-Rawa. Okay, so here we have some reference sites, so some more information can be gathered here. And here you can have some more sound files for Tung-Rawa in particular. And this is the toolbox, MIDI toolbox manual that we presented in a few slides before. That's all. Thanks a lot for your attention.
Yeah, I wondered perhaps if it might be more appropriate to map the data to rhythm rather than melody, because it looks as though your earthquake information is more or less cyclical. So really the amplitude and the frequency are going to be the things that give you the most information, I would guess. I wondered if perhaps it was more suitable for perhaps drums, which may be intensified.
Mm-hmm. Yeah, thanks. Well, this is just to give an idea about what could be done using that kind of music representation of scientific data. So the basic idea is to try to think of a musical way to look at the data. So you have, of course, the possibility to fully customize your melodization. So even choosing the notes in the musical scales that you want to use, you can even fix, for example, some particular meaning, for example, for regarding the duration of the notes. In that case, I just fixed a regular pattern for the rhythm, but of course you can fix, for example, you can set a variable length for the notes according to the amount of the jump, so that you can have an immediate feeling about how your data are scattering up and down, or how large is the jump. And this is just 2 examples. Of course, you can connect other quantity, like, for example, the position of the note in the space, the timbre, and so the stress on the note, so the intensity, and so on, according to other parameters, other physical parameters that you would like to enlighten in that case. So this is, if you want, the simplest way to convert a set of data into a set of notes, so a melody in that case. But of course, you can imagine that it opens a real complex words, multidimensional words in scientific data representation.
When you express the data from the sensors as tones and music and then did a spectral analysis, what difference was there that you added from doing a Fourier transform from time domain into frequency domain?
Well, basically what we did studying, so comparing the two spectral evolution is just to use digital Fourier transform to gather time by time the spectra and compare compare the two spectral evolution in time. So basically it is a fast Fourier transform, a digital Fourier transform, and what we did is just a comparison of the peak, so or better of the peak evolution with time. So trying to study the pre-eruption phase of one volcano, the pre-eruption phase of the other volcano, and look at the spectrum, so the DFT spectrum, and look at how these two spectra, for example, are evolving. So which are the similarities, which are and what is different in the two evolution. So our machinery is intended to automatically carry out the fast Fourier transform and comparison phases together. So a sort of automatic way to gather the information from the volcano, create a digital Fourier transform, store it to be retrieved in the future, and use this peak information to be compared with others coming from similar situation but with different volcanoes. So try to learn how to correlate this spectral information with the eruption phenomena. It was time synchronized. So I just played a little bit with volume to listen a little bit more one of the other. So they are time synchronized. So actually they were playing together. So what I did is just to play a little bit with volumes to listen a little bit better the first one or the second one. But the main reason is because they were covering exactly the same region in frequency. If we can associate, for example, a really high high tone instruments for one volcano and a really low frequency to the other one, of course they are naturally distinguished in frequency and we can play together. So it is just to make it more clear the separation of the two ones.
Yeah, maybe one visionary or obvious question. I mean, one of the expressiveness of music are the harmonies, and have you ever thought of mapping harmonies to your data? I mean, having the harmonic state of...
No, but of course it's one of the next steps. So, so to work vertically, so trying to convert into timbre and harmonic information some particular or some physical information that we want to represent with music. So harmony is a really really effective way to put together more than one information at the same time. So we can superimpose the information. Our human ear is able to make fast Fourier transform, so it is able to distinguish peaks in frequency, and so it is really effective way to map into sound complex and multidimensional data. So that's why I was using those two words, multidimensional and complex data, in the first part of the presentation.
Have you done any experiments with listeners to see if they can actually discern any differences between the outputs from the two volcanoes?
Not yet, not yet.
Not yet.
No.
But you plan to?
Yes.
Yeah.
So that's why we have also the Conservatory of Music as one of the partner, and so our plan is to use both trained musical trained listeners and not musical trained listeners, and also to make a comparison between these two different sets of.
Because one of them plays piano and the other one plays guitar, it should be easy to know which one.
So I missed the question.
That wasn't a question. I was just saying that as long as they play different instruments, it should be easy to know which one's it.
Yeah.
Is there a last question? Okay, let's thank the speaker again. Okay, so the last speaker in this session is Arpad Somoru. And despite the name, he is from the Netherlands, where he got a PhD in astronomy from the University of Groningen. He's now the director of data processing, research and development at the Joint Institute for VLBI in Europe, JIVE. He has a background in radio astronomy, working with radio astronomy both in the Netherlands and also from the US, the Lake Observatory.
Okay.
And he will be telling us about how the high capacity, high bandwidth research networks are becoming part of an infrastructure that can actually help analyze radio signals from outer space and do it much faster and with higher precision than we've been able to do previously. So please, Arpad, tell us about it.
I don't want that one. That's better. So I have 50 minutes? What is it? Sorry. Well, okay. I'm the last speaker, come on. How does this work? There you go. Okay, hi. My name is Arpad Somoru. I'll be talking about eVLBI and how we've been using high-speed networks over the past few years. First, the acronyms. JIVE stands for the Joint Institute for VLBI in Europe, and VLBI stands for Very Long Baseline Interferometry, just to get that out of the way. I'll be talking a little bit about also the principles of EV and how we do this astronomy, just to remind you of stuff that you probably know, but may have forgotten. Stuff that astronomers take as normal doesn't necessarily have to be obvious for other people. I'll talk a bit about the proof of concept project, about the Express project that we're involved in now, EC sponsored project. I'll talk a little bit about satellite tracking, which is an interesting sideline we've been involved in the last few years as well, and about a software correlator on the grid. So the EVN is the European VLBI network. A few pretty pictures. It's European in the broader sense of the word, that it has collaborations all over the world, basically. We observe about 100 days per year, not with all telescopes, with subsets of the telescopes. Until very few years ago, the data were recorded on magnetic tapes. Nowadays we use hard disks, and we are already using the internet as well. These tapes are then processed at JIVE in Dwingelo on a custom-built supercomputer. These are in principle all the telescopes we could use. Of course, many of them I use not for astronomy, but for geodesy, which I'll talk about a little bit as well. So it's really a global network. This is the nice PR picture with all the pretty photos of the telescopes, not all of them. And in the middle, you see how our processing center used to look with the tape units. It has changed since then. This is a few years old. Just some basics again. Just the spectrum. What are we talking about at all? The electromagnetic spectrum, as you can see, the optical bit here, which is where the sun puts most of its energy anyway, which is why we are sensitive for it. About 400 to 700 nanometer, while radio goes from about 1 millimeter all the way to several hundred of meters. Long wavelength, the very short wavelength. And some more basics. If you looked at our galaxy from the top, we would be about here, would be a spiral galaxy. From the side, it's a flattened disk, of course. And several billion stars, gas, dust, revolving around the center in about 200 million years. So if we are sitting in the disk, in one of the arms, and if we look at the galaxy, then we look into this disk. So you get some very different pictures already. If you look in the optical, well, you see stars, basically nearby stars. This black bit is not because there are no stars, it's because there's dust. But if you look at 1.4 gigahertz, which is the frequency of neutral hydrogen, which is the building block of stars and of our galaxy, you see a completely different distribution. And over here you see radiation at 408 megahertz, which results from highly energetic particles, which have been, for instance, created in supernova explosions. So you see two completely different parts of the evolution. This is the building block of stars. After they've been created, burnt out, exploded, you get this. So even more wavelength, you get, neutral hydrogen, molecular hydrogen, but you also get cold gas, hot gas, in the infrared. There's a whole, and every frequency gives a window into a unique physical aspect of the galaxy and of other objects in the universe as well, obviously. Some more basics. In radio, it goes, the resolution will get better as your dish gets bigger. So you try to make it as big as possible, and at a certain point it gets too big, you can't handle it anymore. This is about as big as it gets, 300 meters. It's a valley on Puerto Rico, and it's covered with reflecting material. The receiver is hanging from these big poles, and it can move a little bit. The disadvantage is obvious. You can't tilt it, you can't aim it, or just a tiny little bit. This is about as big as it gets, I said, but there's one being planned in China right now, which will be 500 meters about. You may remember this one from a James Bond film, actually. Then it was filled with water and was blown up at the end. No? It's Pierce Brosnan. So the next step, you can use interferometry, which will allow you to simulate a telescope of the diameter of the projected base length. So this distance between the telescopes. Interferometry, this is if you were looking at a optometrist chart somewhere in the universe, radiating in radio, and you look at it with a very big aperture, you get this very nice, clear, contrasty picture. If you only had this aperture, you would lose all your detail. If now you do make a circle of apertures, it gets a bit better, but actually if you put them in a random pattern, you get by far the best result. And luckily for us, most telescopes are spread in something like a pattern like that. So the two first examples of building a telescope like that is the Westerbork array in the Netherlands, which has a few movable telescopes like a kilometer further off. And there's the very large array in New Mexico in the United States. And you can see, I suppose, this track over here, which is the telescopes can be physically lifted onto a transporter and driven out to new positions up to a distance of 30 kilometers to a diameter. So it makes kind of a giant zoom lens. This is the most compact configuration. And of course, well, you still can go on. You can stick telescopes on different parts of, on different continents. But then, the problem is that then you have to record it. You put in time signals with atomic clocks. Well, here are still the magnetic tapes. And it's sent to a correlator, in this case to Jive, where it's correlated. But even that is, you don't need to stop here. You can put a telescope on a satellite and make, this thing has flown actually. It was a technical mission. It's still flying, of course, but it doesn't work anymore. And a new mission is approved and will fly, I think, in 2012, which will be a science mission, so it will have a bigger dish and better receivers. So this is really the highest resolution of any instrument on Earth. There's nothing like it. So the kind of stuff that we do, just a few examples. This is as close as you can get to observing a star in radio. What you see over here is inside this lighting bit is a star, an old star evolved, has swollen up enormously, is shedding mass. And in this material that is being ejected, under the right circumstances, you can get maser emission, which is the radio equivalent of laser. Very, very intense monochromatic radiation. And so like this, you can follow the material as it is being pushed out of the star, which is you can only do this with VLBI for sure. Another thing, supernovae in different galaxies. Another galaxy, this one's one from 1993. The optical picture and location, and you can see it was followed from 93 until 2000 on this picture. Of course, it's still being followed, and it makes a nice movie as well. There's unfortunately no sound, but so this is tracking the expansion of this supernova shell for 10 years. And of course, the speed that it does so, and you also have information on the front and the back side, how far they expand, gives a lot of information on the interstellar medium that it interacts with. It's a shock wave that's expanding into the interstellar medium. And the physics of the star, what kind of star it was, the physics of the explosion. Finally, a little bit about geodesy. I just mentioned that before. This is the Earth in a potato shape. It's, of course, bent out of shape by all kinds of processes. For instance, the post-glacial rebound. Many parts of the Earth are still coming up after the glaciers receded since the last ice time. So there's all kinds of influences that cause the Earth to have a different shape, and also to change the orientation of the Earth. And that's, of course, very important for, well, for instance, for satellites. You have to know where the Earth is exactly if you want to know where you are. So that's, and using VLBI, you can, if you take a reference frame which is fixed in space, in this case they use quasars, which are very bright, very far away, so they don't move. And then you can turn it around and you can track the movement of your telescopes on the Earth by millimeters per year even. So you can see also how the plateaus, how do you call them, the schollen of Earth move, and also how the orientation of the Earth changes. So that's a big business. Something more about what we have been doing. Well, these are the prices. This is a logarithmic scale, by the way, of disks, simply computer disks. This is what we used to use for recording. This system was designed 15 years ago. And you can imagine how 15 years ago you could store 1 terabyte. There was simply nothing else than using this kind of tapes. And what you can see around this time, it was beginning to be sensible to move to disk recording, which we did. And these are just standard disks from an office PC. It's basically a Linux box with some hardware. It was developed at the Haystack Observatory in MIT. And of course, once you have that, you have a file on a disk, and you can even FTP it. So it's very fast. We started thinking of doing VLBI differently. So this is a very old picture of the Xeon network, the first one, going from a 34 meg to a sizzling 2.5 gig. And of course, it was pretty clear that we fit each other very nicely. I mean, these are all the telescopes in different countries. These are the countries that participate in Xeon. Natural application for this network. And so we started this proof of concept project, which led to this network. There were, of course, SurfNet had to provide us with the ability to get these signals over to Dwingelo, which is over here. And this is Amsterdam. I mean, we demonstrated that we could do it. We saw what the problems were, and it also put the foundation for the next step, which is Express. And you can see the European flag appearing over here, if my EC science officer is over here. And of course, the contract number. So we started this last year, 2006. The main things were to upgrade EVN to real EVN, so to make it real time. You can imagine that the system, which has been designed to work on with tape technology, has not, well, nobody even in their wildest dreams ever thought of sending this stuff real time. It was simply not at all designed for it, so that gives some problems, of course. The inclusion of the E-Merlin telescopes. The E-Merlin is a UK version of VLBI, so it's a number of telescopes spread over the UK Isles. And also to go beyond 1 gigabit per second to 4 and even 10 gigabit per second, and also try to get higher capacity by distributing on the grid. So a little bit of a science talk about why we would be wanting to do this. This is about X-ray binaries, which are very nice to observe. These are very rapidly variable, so you need a very rapid response. I'll show you in a moment what that means. And also future observatories, for instance, LOFAR will be looking at all of the sky all the time. There will be lots of transients, so things that explode, things that happen very fast. You will want to be able to do follow-up on that at other frequencies. This is the normal as it used to be. Oh, it still is, of course, for normal operations. So from the moment that you think of observing something until data processing and publishing, that can be, you know, even further, but at least, you know, 7 months is quite normal. And with EVLBI, we've managed to reduce this to a number of weeks. So these black holes in outbursts were, as a test case, first images within 48 hours. We've done better since that time, actually. We can do it even while the observations are still on. We can already produce the results. And a publication within less than 2 months, which is very impressive for EVN science. There's another little picture. Yeah, it works. As you can see, it's an X-ray monitor, which is monitoring all of the sky. So this is the galactic plane. And these are flaring X-ray binaries. So it's in X-ray. You can see it. This is the date going on. It goes on for years. And you can see they change on scales of days and weeks, and certainly not of months. So if you want to... So what are these? Let's show that first. It's a pair of stars, one that has turned into a black hole or a neutron star, and the other star is being actually, the material is being sucked into a accretion disk at a very high speed, which gives a lot of radiation as well. High temperatures, and a lot of this material is thrown out again in jets, which move at close to the speed of light. So this gives a lot of radio emission. I say high energy processes are always associated with radio emission. So if you see an X-ray flare, you would like to be able to look at this immediately in the radio. This is with Merlin again, daily images. So it's every day another image. But EVLBI can do 10 times better in resolution. So it's, for these people observing this kind of objects, it's very, very useful. And why you want to do that? Well, they are actually small-scale analogs of the black holes powering the quasars in the early universe. So, but much more nearby, much easier to study on a much shorter time scale. Okay, just to get back to networks a little bit. These are, of course, we want to expand to other places. This is a very important telescope for us in South Africa. There's in China, there are several ones that we use for normal EVN observations also. In the States, of course, there's Australian telescopes. And of course, new telescopes are being added all the time. This is the one in Spain, in Jebes. This is the foundation of a big telescope in Sardinia. Over here is fiber being, trench being dug to the Medicina telescope in Italy. And well, this is about what we can do now. We regularly operate at 256 megabit per second, but actually we can do 512, half a gigabit. We're still limited to powers, you know, 256, 512, 1024. But we're working on that also. Arecibo, that big thing I showed you, which is very sensitive, so very nice to have in your observation, has been nearly unusable the last year. Australia, we're testing right now. We are looking still at the connection between the States and Europe. The Australians have 4 telescopes that are also working together as an EVLBI network now. So. China, I'll talk a little bit more about that in a moment. We have a light path from Hong Kong through Chicago to SurfNet. And in South Africa, the problem is that while within South Africa, a lot of work is going on improving the connectivity, it's still very hard to get to Europe. Well, this is just showing the data rate going up that goes into Jive in typical experiments. And of course, all this is possible also because we have SurfNet 6 now, which was a hybrid network, fully hybrid. Géant 2, also fully hybrid, so we can use LightPath. And the network at Jive is also in the middle of being upgraded. Until now, we had the switch at SurfNet, which was taking care of that. We now have our own switch, so there are LightPath moving all the way straight through Géant to SurfNet to us, and there's also, of course, an IP connection. The Westerbork radio telescope has its own connection to Jive. So this is then the situation that we have now. The telescopes that we can reach at 1 gigabit per second, 2.5 gig, 10 gigabit per second to Metzahovi, and it's improving also. More telescopes are getting better connections. The Effelsberg radio telescope, which is the most sensitive telescope in Europe, is still not connected, but will be at 10 gigabit per second because it will be shared also with LOFAR, which will have an outstation there. And what is that? Well, this is the ABES telescope, which should come online this year. So it's getting quite a big network by now. A little bit about the testing we've been doing over the years. We used, well, of course, we used what we had, let's say it so. We didn't start with designing stuff. So TCP is, of course, fine with its reliability, but not necessarily the best solution. These were some tests we did years ago. This shows the learning curve. Over here, we were trying to get data from Bologna to Dwingelo. And over here, you can see what we got before we knew what the congestion window was. So you see, we found out of it. And over here, we tried to get as much data across Géant as possible from as many sites as possible. Those are the first steps. Over here, you can see also on the Géant weather map. Well, you can see where we started testing. So this spike over here. You can see us lighting up the path from Poland. And actually also a few more that, these were all tests many years ago. A little bit about satellite tracking, which is something we've started doing over the last few years. The Huygens descent tracking, I don't know if people recall, it's a Cassini probe which is still circling Saturn. And the Huygens lander was an ESA project and was supposed to land on the moon, on Titan, a moon with an atmosphere, this, on a parachute. And we were asked to track it. So, well, I don't know if you remember these pictures, these really impressive pictures of riverbeds of methane, and it even managed to land and went on happily taking pictures for several hours. So, what we did, we tracked it. The thing had, of course, was sending data back to the orbiter, but we could track the carrier signal of the thing, which has the power, more or less, of a mobile phone at 1 billion kilometers, at an accuracy of about 1 kilometer, which is pretty good. And of course, you also get Doppler information, how fast it goes towards and away from you. These are little blow-ups of these 2 points. And it actually has so much detail that you could even get the parachute flight dynamics out of it. So say it came down like a pendulum, so you even can get that movement out of the data. So it was a fairly big success also because it saved this Doppler experiment, which went wrong. For this we used actually, to transport part of the data, we used our first light path also, which was set up by ARNet and Canary. And we tried to do this again with the Smart 1 satellite, which was crash-landed into the moon. Well, crashed into the moon. So at the end of its mission, this was a European probe also. Well, just to show you what a spacecraft spectrum looks like. It's very narrow signals. And that you can do some really interesting science also while tracking a probe. You can get a diffraction pattern when the thing goes behind the moon, which is kind of interesting. And this is when it crashed. This is an optical picture, bang, that goes. And this is with Tigo in Concepcion in Chile. And the blue one is, fell away, it's Hobart on Tasmania. 2 radio telescopes took a look at it, and you can see the accuracy with which you can see when it stopped working. For this, we had to find out how this path went to Tigo, to South America. Of course, there's the Géant network, the Red Clara, the Riona network, and then it hits the University of Concepcion and the telescope. And when we started, we got 2 megabit per second, and we found that there was a cap over here of 5. Over here, I think it was limited to 90. And over here, it says a gigabit per second, but actually it's 100. So a lot of tests were done by people of Géant also. They really tried to find out what was going on. And what you find out is that this whole piece is fantastic. There's no loss. And then you get to the university where people live, and that's really annoying. Immediately everything goes to hell. So we managed to get it a bit little bit better. And then on the day that we wanted to get the data over, we got 2 megabit again, so whatever. But it was a very useful exercise. Also, we learned to know who these people were, where everything was. So, and the University of has decided to upgrade their network, also partly because of this. So that was a good result. Finally, China. That's very interesting. The 2 telescopes that we're always using already for many years is the one near Shanghai, Sheshan, and this one, Urumqi. By the way, the distances over here, so I think this is 3,000 kilometers. It's incredibly big. These 2 telescopes I regularly used. This one is in a very good position to do EVIL BI with as well, because there's a 1 gig connection to Shanghai itself. And then there's this 2.5 gig to Beijing, and 2.5 to Hong Kong open exchange point. And from there, there's a light path to Holland. There's of course the Orient network, which we can't use right now. This telescope, although it says 1 gig, this is a new one. They just built this. They're making this network to track their lunar probe, which is going to go up this year, I think. So this one is nearly finished, but we can't use it yet. This one I don't even know the status of. And this goes along, this is our light path. It's 360 milliseconds. It's kind of long. I mean, it would be nice to go the other way around, but. And we're testing on that. Okay, I'm just showing you a few results of tests. This was all the way from Jive to the telescope, I think, or at least Shanghai telescope. Okay, and you can see there's a lot of packet loss. It shows packets sent and received per round trip time, and you can see the AX, the SAX, and the double SAX. This is a blow up. This is a startup of the connection, which you can see over here is the slow start, and then the big start takes over. And over here, it seems that the kernel decides that it's only going to acknowledge every second packet, and then slows down again a bit. And over here, you hit congestion. Here, you lose a packet, and then you get into the congestion avoidance. So this is pretty bad. At least it was. We found out also that most of the packet loss occurred from Hong Kong to Beijing, I think, right? Over here, though, you see from Jive all the way to Hong Kong. So this is a pure light path. It wasn't 2.5 gig, which we thought. It's 622 megabit per second, but okay. And this is simply limited by the congestion window size. It's 340, completely without any packet loss. It just runs on TCP. Since this picture, actually today we heard some results of our colleagues in Shanghai are testing now the link, and they've fixed something because we now get nearly 800 megabit per second between Hong Kong and Shanghai. So it's actually beginning to look very good. Finally, only 2 slides more. On Fabric, which is as I was talking about, the correlator that we use is a purpose-built supercomputer. It actually runs about 40 teraops, which is really a lot. If you compare it with other supercomputers, the LOFA Blue Gene, the IBM thing, reaches 27 teraflops. Of course, this is comparing ops with flops. These are 2-bit operations. If you want to go to anything bigger for the future, you know, we want higher bandwidth, we want, because you get better sensitivity, more stations. Well, this 640, I suppose you could bring it down to 200 teraflops. So if you change the architecture. But anyway, one way of doing this might be to use the grid. So what we also, part of the Express proposal, is doing a pilot on the grid, using the grid. As you can see, SETI seems to be getting 59 teraflops. So there's a lot out there. This is like a representation of how that would work, all the different things that have to be taken care of. But the main thing is then this Fabric could be either a grid-based thing, or it could be a supercomputer, or what would be really nice if you could decouple all these things and stick in anything over here. Another representation of that is how you could do it. You could time slice the data, or frequency slice, probably time slice. And that's what we have been working on also for the last 1.5 years. So this sums it up, kind of. We're trying to get to a production EVN network. We have now 4 of the 6 working telescopes right now have dedicated light paths. And which of course gives you, well, it's really very nice for not having any congestion, especially when CERN, when the LHC comes online next year. This might actually begin to be a problem on Géant as well. And we could think of different configurations of telescopes, so you can offer a certain number of telescopes at a certain data rate to users, because it doesn't look like all telescopes will be as well connected as all the others. So. But anyway, we're well on our way of getting a real connected element interferometer. So the last PR picture, all the participating telescopes. And that's it.
Are there any questions?
One question concerning the network transport. Are you using, or do you have people working on efficient compression schemes for these
Compression schemes?
Compression schemes for these amounts of highly correlated data?
No, the data aren't correlated. The data is noise. It only gets correlated at the correlator. So it's more than 99% noise. You have to filter the signal out. So there's no compression possible at all. So, but we can lose a fair amount of data without suffering. So that's the advantage.
Sorry, just you said it was 300 millisecond latency on the light path from chamber.
Round trip time 360. 365 even.
65.
365.
Yeah. Where does the latency come from in that system?
Well, the physical path length is pretty enormous. It goes the wrong way around the world.
So it's just the speed of light that's causing it. Yeah. Okay, thank you.
I have a question myself. What do you think will be the biggest impact from this technology going from ordinary VLBI to eVLBI? And when you have the light paths and can do it at the high data rates, will it be just convenience? Will the scientists be able to do new research?
I should have said a bit more about that. One of the things, of course, is the rapid response, which makes EVN a completely different instrument. I mean, if you go from having something that takes months until something that you can do within 2 days, that of course gives different scientific possibilities. But the potential for higher bandwidth is also that you can, as receivers become better, you get a higher, well, you want to observe a bigger frequency slice because your sensitivity goes up with that. And, you know, it's nearly unlimited in theory. You can go to 10 gig, 40 gig, well, you have to build the receivers, of course, but it's not very likely that you can record that on the disk. I don't think you can record 10 gigabit per second on the disk. So it kind of frees you from the magnetic media and opens the way for much higher sensitivity, which opens the way to, you know, observe much fainter sources, of course. So.
Sorry. Okay, I think we should thank all the speakers of this session. I'm from UNICE, and I will be chairing this session, which has 3 speakers. The session is entitled Networks for E-Science, from the depths of the oceans to the depths of the universe. And of course, if you read the program carefully, you know what lies in between the depths of the oceans and the depths of the universe. That is music from the volcanoes. So I think this will be a very exciting session about some of the projects that use the infrastructure that the research networks provide. Our first speaker today is Martin Beck, who has a Master in Engineering and is the Deputy Director in UNICE, where his division is responsible for, among other things, the development and operations of the Danish Research Network and also some of the commercial businesses of UNICE. Martin has been involved in many pioneering projects involving networks here in Denmark, among other things, setting up the first commercial internet service provider in Denmark, deploying nationwide services to schools, and one of the last projects also the health network. And Martin will be telling us a bit more about the Galathea 3 expedition that we heard about in Catherine Richardson's talk, and he will give you some more technical details. So please, Martin.